This quick introduction to stock and flow modeling isn't going to give you everything you need to know or can know about stock and flow modeling. So if you want to use this technique as a more rigid engineering technique, I would refer you to other sources. But if you're like me, you're often looking for a very fast, easy tool that you can use to help you understand the flow of what's going on in a system you're trying to model, and in particular during the opening stages of a project, to try to figure out exactly what the essence of a project is, because many systems projects boil down to the management of one or more stock and flow scenarios as they go through. So I almost always start an engineering project by developing a stock and flow diagram for those perspectives of the system I'm interested in that lend themselves well to that. Thinking about that, there's a conventional example you can use for illustrating a stock and flow, and the bathtub is the classic one everyone uses for modeling and for teaching the technique, because a bathtub is your classic stock and flow scenario where the bathtub is itself a stock of water. You put water in, you get water out. So you know you're looking at a stock if you're looking at a thing such that you would be interested in modeling it from the standpoint of it being more or less of something. It can be empty, it can be full, it can be things in between. But if you're managing something that's going up and down in terms of its level, you're probably looking at a stock. And that doesn't necessarily need to be a physical stock, but it often is a physical stock as you go through. So when we draw them, we typically show the inputs as flows going into the stock, and we also have flows that will come out. This is just a depiction of kind of one classic way you'll see it drawn in the literature, where the input or the output flow is given some kind of a valve like a faucet. Again, going with that bathtub kind of scenario that many stock and flow thinkers think in terms of. The valve is your depiction of a point at which you could control in your engineering the rate or the types of inputs that are going in. Also, the cloud effect to the left shows that sometimes you don't care or know where the flow comes from. It's not part of your modeling scope to pay attention to where it comes from. So we often depict flows coming from a cloud or going to a cloud to depict the fact that we're not interested in this scope of what's going on out there. The problem you run into is that these conventions can make drawing a stock and flow diagram rather tedious. So more often than not, I omit them from my thinking, but I wanted to show them to you because in the literature, you'll often see some depiction of that as you go through. So the way I quickly draw these things, I would get rid of those conventions, and I might go with something like this. If I'm looking to model the bathtub as a stock of warm water. So bathtubs hold warm water for us, and water is an input. So I've omitted the cloud, I've omitted the faucet valve, but they're implicitly there whenever I'm drawing a stock and flow diagram. Also, I keep track, because I'm using this for engineering, I want to keep track of the level of systems modeling that I'm interested in. So this particular example, I'm interested in the bathtub as a stock of warm water. There'll be more or less warm water in the bathtub. So I'm going to view the system as a mechanistic system of providing that function of warm water as we go through. So this depicts water as an input. And therefore, I'm going to need a drain for it to come out, because the central premise of any stock and flow is that you ultimately have to account for what goes into the stock. If something goes in, it has to come out. Nothing that comes out can come out unless it went in. So you have a certain conservation of flows you want to be thinking in terms of. And that's one of the essential things you should be thinking about when you develop a stock and flow diagram. It's what are all the ways your stock content can get in, and what are all the ways it can get out, and have I actually accounted for the entire gap. So a bathtub could be modeled at the level of water in, drain out, and at a mechanistic level that kind of satisfies what a bathtub is, if you will. But from an engineering standpoint, if I want to design a better bathtub process as a stock of warm water, it certainly is not enough. So your first inclination for the stock and flow might be overly simplified. Many of my students draw stock and flow diagrams with just one input and one output per stock. If that's all you've got, chances are you didn't need to develop a stock and flow diagram. Usually there's something else going on as you go through. So I might ask myself, what else is going on when I'm looking at a bathtub in terms of it's controlling it as a mechanistic system that is a stock of warm water. And the first thing I might realize is it's not just water that goes in, it's hot water versus cold water. I have a separate spout for each. So they really are separate inputs, because the way I'm going to control the temperature of the water in the bathtub is I'm going to vary the amounts of hot and cold water that I put in as I go through. Likewise, I need bathers in the bath. The bathtub, when it does have warm water in it, is going to get a bather get in. A dry bather is going to get in, and a wet bather is going to get out. Now that's not warm water, but the presence, the displacement of the bather in the bathtub affects how much warm water the stock can have, and therefore it's quite relevant to my discussion. If I were to fill the bathtub to the top before the bather gets in, I'm going to have an overflow because of the displacement of the bather getting in. So I can't talk about the bathtub as a mechanistic system of water unless I also include the notion of dry bathers getting in and wet bathers getting out. One of the reasons I have to show the wet bather getting out is that the wet bather takes some water with them as they come out. So the water that comes out on the bather and has to be drawn off with a towel does not go down the drain. So to truly account for all the water in the bathtub, I need to know that the wet bathers are coming out and some of the water is going out with the bather. Likewise, I said before, if the bather gets in the tub and the displacement doesn't allow for the stock to hold enough water with that volume, I might also need, and most bathtubs have, an overflow drain, something that will drain off water if the level of water in the bathtub gets too deep as we go through. So it's not just the main drain, but also the overflow drain. Likewise, I'm going to have some evaporation. And in most engineering contexts, I would imagine that the evaporation rate from a bathtub is not going to be consequential. But if I truly want to account for all the water coming out of the stock, I should at least consider evaporation as I'm going through. And likewise, if the person taking a bath does a lot of spilling and splashing, some of the water might come out of the tub over the sides as spills and splashes going on. So the actual input and output flows from a bathtub aren't particularly complex, but they tend to be a little more than I might have realized when I first sat down and started my discussion. And that's the real power of stock and flow diagrams. They're easy to draw, they're easy to check, and they quickly show you that the problem you're dealing with as an engineer is probably a little more complicated than you thought it was. So the earlier in your project you realize that, stock and flow is something I do in the first couple of hours of a project, not the first couple of days, but the first couple of hours as I go through. Now, having drawn and accounted for all the inputs and outputs, I also tend to annotate the diagram with additional factors that I think are relevant to understanding the context of what I'm trying to do. And I do that by usually noting things around the model that I would want to measure and where I would want to measure them. So in terms of the hot and cold water coming in, I'm interested in the temperature of the water and the flow rate of those faucets. For the dry bather, I'm interested in the volume of that person for displacement purposes. The bathtub itself, I'm concerned with the volume for knowing how much water it can hold, as well as surface area for knowing how much evaporation might be and how quickly I'm going to lose heat as a result of the water being there. On the output side of the main drain, the overflow drain, I'm concerned with the flow rate. For evaporation, I'm interested in the ambient temperature and humidity of the room. So it's whatever I can think of that represent some key measures of what's going on here. I want to get those annotated on the stock and flow diagram. And that's useful to me as an engineer because it helps me anticipate those things I'm going to be looking at and trying to optimize as I see my way through. So I can tell already, just for a project that's going to pursue designing a better bathtub process, is that I'm going to be very concerned, particularly with hot water. How can I control and emphasize the temperature of my inbound hot water? What kind of water pressure do I have on those things? How good are my drains? So, we think in terms of engineering, always plan your maintenance on day one. So keeping those drains cleared so I maintain my flow rate is going to be very, very important as I go through. The surface area of the water and the volume of the water, again, is very, very important for being able to maintain the temperature of the water over time. Now, this is a mechanistic system, so I can think of it in those terms. But as I start to think about it more deeply, I start to think in terms of not just a mechanistic system, but because I have a bather coming through this process, I've got a human being coming through this process. So it's really going to turn into not just a mechanistic system, but it's going to become a societal system because every bather is going to have their own preferences for how warm the water should be, how deep it should be, things of that nature. As they go through. So in order to really understand the system, I can't just model it as a mechanistic system because I've got people coming through it. I'm going to also need to model the bathtub as a societal system as well. So if I'm going to do that, I'm remodeling the bathtub now, looking at it not just as a stock of warm water, but as a stock of bathing capacity. So do I really have the ability for people to bathe in my bathtub? So again, when I draw it from that standpoint, again, water's coming in, drains are coming out. Since I'm being societal, not mechanistic, I'm not going to get bogged down in the hot versus cold at this point because I have my mechanistic model on the prior pages. So I'm just going to model what I need to understand for what's going on with individual bathers. So I can take my dirty bathers and my clean bathers. In the mechanistic model, they were just dry and wet. In this model, getting clean and bathing in the tub, it becomes the point. So my dry bather is now a dirty bather, and my wet X-ing bather is now a clean bather as I go through. I also have certain consumables that will be needed that aren't part of the mechanistic use of the bathtub, but they affect how the bath is going to be worked. So the soaps, the shampoos, the washcloths, the sponges, maybe the toy boats if I'm dealing with children. All those consumables affect what's going to be going on inside that bathtub. So they affect the capacity and the ability to do bathing. And some of those things have waste. Empty bottles, used up soap, things of that nature are going to come out as wasted consumables. And because they're consumables, they might not get used up every time there's a bath. So I'm on to show that some of the consumables in the bathtub continue to be used until they're used up. So a bar of soap might last a week or 2 weeks going through the process. A bottle of shampoo might last a month. But one way or the other, I have to account for the consumables coming in, them being used, and the waste coming out the other side. So this is the view of the bathtub as a societal system, where I'm no longer looking at how the bathtub works for keeping warm water moving, but how does the bathtub work as a societal system for letting people bathe. So, again, I can add my measurements to this as I go through, just things I think are going to be important. The temperatures and the flow rates are going on. And one of the key measures in the social process of taking a bath is how long does the bath take. So the duration of a bath has a big impact on the temperature and temperature flows. It's much easier for the mechanistic system to deliver and maintain warm water if people tend to take very fast baths. If they don't take very fast baths, we're probably going to be back in the mechanistic system and having to add more hot water to the tub before the person even finishes bathing. So there is a relationship between these two models, but they are very different models. Don't try to do all of this in one model. Don't try to model mechanistic components of your system as part of your societal view. And don't try to model your societal view as part of your mechanistic view. These are both legitimate viewpoints on the bathtub system that I would want to capture. So models like these allow me to capture that very, very quickly and very, very early in the process. That's the real value of stock and flow diagrams. As you move into your engineering, it gets even better when you move toward your system design and your architecture, because the inputs and outputs become the components of the functional architecture that the system has to satisfy. Again, you and I know how bathtubs work, so we can already imagine how all of this is going to work. But imagine doing this for a system where you don't know exactly how the system is going to work as you go through. So let's take a look at another example. How about your refrigerator? The refrigerator is mechanistically, it's a stock of cold air that you put to use. Remember, mechanistic systems provide function, they don't have purpose. So the function of a refrigerator is to supply cold air around things. So we can model how that works as a mechanistic system using stock and flow diagrams that we go through. So we're basically going to take chilled air. It's really air that's already in the refrigerator coming off the compressor plates. So they're being chilled by the compressor at the bottom of the refrigerator. But we're basically moving chilled air into the refrigerator. But we're also loading our warm content. If all we did was put cold in the refrigerator, it wouldn't provide much function. It's really a matter of the things we put in the refrigerator that are not cold, that we want to make cold. So we put in warm content with chilled air so that we can remove cold content whenever we want it from the refrigerator. That's the basic mechanistic function of the refrigerator as you go through. Now, you can't just have cold content, because the reality is even if you never take anything out of the refrigerator, periodically the air inside it is going to lose some of that chill. So you're going to have thermal loss as you go through that you need to account for. That's the reason why the refrigerator might have to turn on periodically as you go through. Also, you've got air loss from inside the refrigerator every time you open the door. So you open the door of the refrigerator, a lot of the cold air comes out. You close the door. Now the refrigerator has to make more chilled air to bring the temperature back down to where you want it to be. So you've got some real competition and throughput going on here in terms of what's going on. So I can add some measures to that. I'm very interested in the temperature settings for the cold air. What's the actual temperature setting inside the refrigerator? What's the volume of the refrigerator? Because I want to know what's the volume of food coming in and out and what's the real temperature. So ultimately, refrigeration as a mechanistic system becomes an optimization. we want to minimize the amount of extra space inside the refrigerator. We want to fill it up with warm content, because the fuller the refrigerator is, the less cold air there is to pour out every time we open the door. Conversely, though, if we overfill a refrigerator, we don't get appropriate airflow within, and the incoming chilled air doesn't circulate. We get super cold sections where things freeze that shouldn't freeze. We have other areas that are warmer than they should be. We don't want that. So we want to keep the content low enough that the air can circulate and keep the ambient temperature inside the refrigerator constant. But we want to have as little extra space as possible so that we don't lose a lot of our cold air every time we open the door. So for any given household or any given way of using the refrigerator, there will be an optimum refrigerator size. If you tend to have a lot of food in the refrigerator, you can justify a larger refrigerator. But if you tend to keep nothing in your refrigerator, you shouldn't have a large one, because you're just going to pour cold air out on the floor every time you open the door. So again, that's the social context. We can model the mechanistic systems of stocking the cold air, but ultimately whether this mechanistic system function is put to good use or not isn't a question of the mechanistic system itself. It's a question of the societal system with which it is embedded. So most mechanistic systems we're interested in as system engineers actually provide their function to the social system. And it's usually, as systems engineers, it's the societal system that we're usually more interested in. So let's take a look at the refrigerator not as just a stock of cold air, but as a stock of cold food that people want to eat and drink and consume on a societal basis. So what's the societal purpose of the refrigerator as we go through? So again, we want to put new content into the refrigerator, and we want to consume the things that are in the refrigerator that we can take out. So that's its underlying purposes. Put stuff in to stay cold till we want it, and then take it out and consume it. But we also find that sometimes you have got to basically get rid of some of the stuff that's in the refrigerator. It gets old, it gets stale, sometimes it gets freezer damaged. Any number of things can happen. But ultimately, content goes in, and we have either scrap or consumption coming out as we go through. If we attach our variables to that, we find the refrigerator has its temperature and its volume become important even to the social function. The variety of new content going in has a large impact on how the refrigerator will be used. That scrap content is a function of the age and freshness and freeze damage and even obsolescence of the food that's there. Sometimes you just get rid of food because it's been there too long. The consumption side really drives your meal choice and diversity. So those are variables on the social system side that dictate how the refrigerator will be used. And when you're doing a stock and flow diagram, you're not limited to only doing measures that point to the individual components of the diagram. You can actually add measures that allow you to look at some of the relationships and feedback loops among the portions that are there. So for instance, you might say that to the extent that there's certain foods you're often scrapping, you might want to use that knowledge to drive your meal choice and diversity. So if you have things in your refrigerator you know are approaching their expiration date, maybe you should plan some meals where you'll use that food. So use it on the consumption basis, which is value adding, as opposed to the next day or the next couple of days having to scrap it as waste product. So you can use the freshness and obsolescence of the food in the refrigerator to try to plan your meal choice and diversity as you go through. Likewise, as you expand your meal choice and diversity, that might cause you to change the way you shop. The things you buy at the store might need to change based on what you're learning from your use of the refrigerator. And so you've got feedback loop built in there. If every week you scrap 3 bananas, then you might want to modify your shopping list every week to buy 3 fewer bananas as you go through. Something as simple as that going through. So your societal system is the use of the function that's provided. So you often have a mechanistic view of the system you're working on, plus a societal view of that mechanistic system in use. And as a systems engineer, you're interested in both levels. And in particular, you're interested in the societal view. How do people make use of systems to provide value and make things work? So stock and flow diagrams can be done in a much more rigorous way than this. If you're interested, look at Donella Meadows' book on system thinking. It's a great book for looking at stock and flow diagrams. But there's lots of extra stuff you can build with stock and flow diagrams. There's lots of additional, more rigorous techniques that people might apply to them. And I urge you to pursue those. But that's not what this little lesson was about. This lesson is about just learn to use stock and flow in this very rudimentary way so that you can get just enough of your system idea down on paper that you can start to see the important measures you're going to manage as an engineer, as well as the very critical distinction between a system as a mechanism mechanistic functionality versus a purposeful societal system that people are making use of. As a systems engineer, I'm concerned with how people get clean using their bath, how they prepare food out of their refrigerator. And that's important from a systems standpoint. A mechanical engineer in me, the electrical engineer in me might want to analyze exactly how the refrigerator works, or exactly how the bathtub works. But for the most part, I'm interested in the societal view of systems. If you take just the few minutes it takes to draw these diagrams, they can often be drawn by hand on a single piece of paper. You'll find it really helps in the way that you scope out your projects and start to approach them moving forward.